the thinking is, well, it's theoretical, obviously, but we could be a unique universe where everything's in a balance.
Yeah, the alternative to the multiverse is the idea that the universe and the Higgs field and so forth is stabilized. The things that make it unstable are basically canceled away by the existence of a whole new set of particles that would match, if you like, match up to the existing particles, but be slightly different. It'd be like a mirror image of the existing universe of particles, or the type of particles that exist in our universe, the ones that we know. You'd have like a mirror image of them, but with some distortion, small distortion. They change slightly. And because of that small distortion, which is just a change in their spin, actually, they exactly cancel out all the instabilities that are produced by the existing particles.
Yeah.
And then the universe becomes very stable. And that symmetry, we call it, one of the main candidates for that symmetry is called supersymmetry. And
Okay, yeah.
that's what we're looking for now. We're trying to understand, does the universe have this supersymmetric character? If it does, then we understand exactly why it's stable. And all these discussions I had about, talking about the instability of the universe and the lifetime of the universe, would change completely. But we haven't gotten any evidence yet for that.
Is it like a temporary phase where everything goes into balance? And is it because is that idea the universe is expanding? Is that still is that still like a notion of what could be happening?
Well, the universe is still expanding, and originally, well, up until recently, it was thought that it was expanding, as a result of the initial explosion, and it wasn't. There was nothing else causing the expansion. But then, in the last 20 years, it was discovered that the rate at which it's expanding is actually accelerating.
Yeah.
And that means there's some source of energy in the universe that is causing it to really be different than we initially thought. That this energy is causing it to expand at an accelerating rate. It may have already been there, the energy, for a long time, but the universe was too dense in earlier periods, and gravity overcame this additional energy. But it was, it's within the last billion years or so that that changed, and the universe started to accelerate very fast. It must have overcome the energy of the gravity that was fighting this expansion. So that's something we're trying to understand. We call that energy dark energy.
So is that dark energy? I mean, it's part of the Big Bang, but it was controlled by gravitational forces for a long time, and the gravitational forces decayed, so the dark energy is out of control now. Is that basically what seems to be happening?
Well, yeah, it wasn't so much that it doesn't really directly interact with gravity necessarily, but you had two forces in the universe, and gravity was stronger when the universe hadn't expanded quite as much as it is now. As it gets more and more expanded, gravity gets weaker and weaker because it's over longer distances. And so now, of course, this other force seems to have got the upper hand. And so, yeah, the universe could continue expanding. Now, but we don't know much about this new form of expansion, or this dark energy. There was, like I said, we're pretty sure that there was a very rapid period of inflation in the very, very early universe that appears to have stopped.
Yeah.
As well. So some sort of transition took place to stop that expansion. We don't know what's going to happen with this expansion because we don't know what's behind it. But it's very likely that if it's a particle, a field made up of particles, then there would be particles with no spin, like the Higgs field. If it were the Higgs field itself, that would be very convenient, but I'm told that the Higgs would not fill the bill, would not be able to explain this expansion. So it's probably some new particle. And in some sense, that's very interesting.
Is that a smaller particle, or just like a mystery particle?
It's really a mystery for the dark energy. It's really a mystery. There's another type of energy, another type of particle that's called dark matter.
Yeah.
And we know that galaxies are filled with dark matter, and that this dark matter was very important to the formation of galaxies. And we see very clear but indirect evidence of it in how the galaxies behave. That dark matter, we think we have some good ideas about what kind of particles make up that dark matter. And I'm in the process, along with many other physicists, of trying to see if we could produce it at the LHC and see the telltale signs of its existence. And that would be a great breakthrough as well. And by the way, supersymmetry, which stabilizes the universe, actually predicts the existence of dark matter.
Okay, yeah. Because I remember you explained to me that when you started work on CERN, etc., that they thought dark matter was 10% of the universe, but now the thinking is it's about 90%, is it, or something? Or
well,
so it's 90%, yeah.
Well, I don't remember what it was that we originally thought it was, but dark matter is yeah. I think it's been understood for quite some time that dark matter is about 85% of the matter of the universe. Okay.
Yeah.
But it's only about 28% of the energy of the universe, or something like 26% of the universe, of that order. Let's say it's a quarter of the energy of the universe is dark matter. There's only about 5% of the universe which is visible matter, the stuff we're made out of. So we're really, really in the minority. Yeah. And then the remaining 70% of the energy in the universe is this dark energy. And
all right, so yeah, it's mainly dark energy is a large percentage, then it's dark matter, then it's the visible.
Then it's visible matter.
Yeah. And you saying, I remember when we spoke, you said the dark matter, it was called that because it was dark and nobody quite knew what it was.
Yeah, it's dark in the sense that it does not appear to be interacting with other particles and it doesn't produce any light. And so when you look out in the universe and you look at galaxies, you don't see it. You infer its existence by watching how the galaxies behave. And what's kind of interesting is the galaxies, you've seen pictures of galaxies, they look like these big spirals, right?
Yeah.
And they're spinning, which is what causes the spiral. They're spinning in the plane around a central point. And people noticed that they were spinning, as you measure the rate at which they spin. Surprisingly, you can actually do that very easily. You can measure how fast a galaxy is rotating by the color of the light coming from the two different sides of the center. Because the light, for the stars that are moving away from you, those galaxies, the light coming from them, those stars, the light is shifted to a slightly different color than the ones that are moving towards you. And it depends on how fast they're moving. And so we can measure the rotational rate of the galaxies as you move away from the center, and we expect it to drop very dramatically because those stars that are farther and farther away are very, very loosely connected gravitationally to the center of the galaxy, right?
Yeah.
Because they get farther and farther away. But in fact, they're moving much faster than you expect, and in some cases they're even accelerating. And so that could only be possible if the whole galaxy was sort of in a pudding of some sort that's actually moving all the stars with it at some level. But that pudding is hard to see. It's we couldn't see it at all.
So in a sense, it's like a dark pudding.
Yeah, it's just an invisible pudding. It's not producing any light.
Yeah.
But the interesting thing that came out in the last 10 years or so was they started looking at galaxies that were colliding. And there are many cases in the universe where you see two galaxies colliding. And then you can actually see how this dark matter is following the galaxies as they move through each other, while the normal matter is still kind of trapped in collision between them. And you can see the effect of this dark matter by looking at stars behind the galaxies further away, and you get double images because the light is coming through maybe directly one way, and through the dark matter creates another path for the light, and you start seeing double images. This is called gravitational lensing. Yeah. So we see this dark matter is there. There's pretty clear evidence that there's something there, but we don't know what it is. And so there are experiments all over the world now, really, literally dozens. Every continent every country, every major country seems to be involved. We're all trying to find out what it is, and we think it's in the room with us right now. We're passing through it all the time. We just don't interact with it. So we're setting up experiments that are super sensitive, that should detect this stuff, and they don't. And at the LHC, this Large Hadron Collider, this big accelerator that we have at CERN, we're hoping in proton-proton collisions we can actually make this stuff. if it's not too heavy, we should be able to make it. And of course, we don't see it because if we make it, it just becomes invisible when it's just invisible when it comes out. But if it's made with something else that's visible, then we can detect the imbalance from the visible and the invisible energy in our experiment.
Well, the normal matter would frame it so you can actually feel it was there. Yeah.
Well, you could produce, for instance, you could produce, suppose two protons collide. That's what we do, 33 million times per second. We collide two protons at very high energy. And suppose in a rare occasion, those two protons produced very heavy supersymmetric particles that decayed. You'd have a pair of them. Each one decays to a standard model particle that we can see and a dark matter particle that we can't. And then what you have are particles in the detector that we see very clearly, but their energy is not balanced out. Something is out of balance, and there must be some invisible energy going out.
Yeah.
And that's how we detect it. There are other processes that do that. There are kind of mundane processes that do that. So we'd have to look for kind of a higher rate than expected, and that's what we're doing. And so far, we have tremendous sensitivity, actually, believe it or not. But so far, we haven't found anything. So we know that this dark matter, if it's out there, we're starting to get a sense that it's maybe a little heavier than we expected. And it's got slightly different properties than we expected, and it interacts maybe a little bit more weakly with normal matter than we expect. But we think it has to interact with normal matter somehow. We think there must originally have been some kind of interaction.
Well, yes. So at one time, at the beginning of the universe, it would have interacted, and it's
exactly.
not but it's not interacting now. Is that what?
Yeah, it must have been produced. We think. Well, there's a chance that it was produced at much higher energy. There are particles that were produced possibly at much higher energy, and those particles all decayed. And it's the last thing they decay to is the dark matter, and it's stable. It doesn't decay. So we just hope that our accelerator goes that little bit higher enough energy. We're going to go to much higher energy actually this coming year. In 2015, we're going to go from 8 trillion electron volts to 13 trillion electron volts of energy. And
yeah.
We're hoping that it might just be there. And that sounds maybe like, we're just fishing in a big, very small part of a very big pond. But it turns out the theories we have, they all seem to point at it being around this energy. Okay? So we're still hopeful we'll see it, and that would be very exciting, obviously, because we'd suddenly begin to know something more about a much bigger part of the time is very long, but it's very uncertain, actually. I'll tell you more about that in a minute. But eventually, we believe that the universe will go through another transition. And in that transition, the Higgs field will change, make a major transition in which then particles would suddenly lose their mass, and atoms would fall apart. And you'd have, lots of energy released in atoms and systems completely disintegrating into individual particles. Yeah. So the universe would just sort of unravel into just a dusty kind of particle-filled vacuum where there's tons of light produced. And so you'd have this kind of bright white light at the end of the universe.
Yeah. So, and that's like an eternal kind of white light.
Yeah, it would be eternal light. The light would just propagate around the universe forever, but the universe would continue to expand, presumably. So the light would get weaker and weaker. So you start with a bright light that just slowly fades away, and kind of like the end of a great performance, if you like.
Yeah, yeah. So we'd actually end up being in darkness once all the lights and the energy had all faded out of the universe.
Yes, and that's kind of dismal, really.
Yeah, yeah. So it's
we don't know. We don't know this. This is an era of human research in which we're first, really for the first time, getting enough data to talk about the whole universe and its evolution. So we probably still don't know enough to predict everything, but we know sort of what are the possibilities, and we need to do better measurements. So, for instance, the stability of the universe depends on our estimation of the stability of the universe depends on the mass of the Higgs boson. Believe it or not.
So that's one of the real keys to the understanding of it.
That's right. So the mass of these bosons is very important. And the mass of the heaviest particle, the heaviest fundamental particle that we've ever found, it's even heavier than the Higgs. Higgs is number 2 in mass. The number 1 particle in mass is the top quark. It's the 6th of the 6 quarks that we found.
Yeah.
And I was actually involved in that discovery. That was 19 years ago at Fermilab in Chicago. And the mass of that particle is even a little bit more important, partly because it's harder to measure to very high precision. The Higgs actually turns out to be a little bit easier to measure. But those 2 particles, their masses tell us where the universe sits. Is it stable or unstable or metastable? And so far, it looks like it's right in the middle of the metastable region.
Yes, it's in a sense that the universe is middle-aged.
Well, it's not so much that it's middle-aged, as it's just sitting. It's like it's sitting between 2 different phases. So it's kind of like, to one side of us there's water. Think of water. Water can be frozen, or it can be liquid, or it could be gaseous. So suppose that you're sitting sort of right at the boundary between liquid and ice.
Okay. Yeah.
And so that's what we're doing. We're sitting kind of right at that boundary, and we're solid, but we're quite close to melting. On the other hand, if you calculate how long it would take, there's a huge uncertainty, but it could be 10 to the 100th billion years. It could be 10 to the 10th billion years. Maybe it's 100 billion years. We don't know. So we need to get these masses measured to much higher precision to narrow down what that lifetime estimate would be. And we think in the next 10, 20 years we'll actually be much more precise about this.
I remember in the conversation we had, and we'll go back to the Big Bang thing, there was the idea that time came out of the Big Bang as well. So in a sense, there can't be a before because there was no time. Was I getting the handle of that right?
Yeah, I'm learning more and more about the universe, and as I'm trying to learn more about the current theories and how the universe is understood. So the thing is that I'm not entirely sure of that statement that I gave you before. Maybe I was wrong, but the idea I understood was that with the Big Bang, you basically, in some sense, you're creating space-time.
Yeah.
And our space-time, if you like, is created. What we have access to. And time itself is really a strange thing, because time is something that we connect to evolution of a state, or evolution of motion of things. And the direction of time we know kind of naturally is the direction in which things get, if you like, a little bit more complicated. If you were to see somebody drop, if somebody dropped a teacup and it shattered on the floor, you would not be surprised. If you saw a shattered teacup on the floor suddenly pop back into a full teacup, you would be very surprised.
Yeah.
And so we have a sense of what is the direction of time based on that kind of notion, that things become, more complicated. They become a little bit more, perhaps more random, more broken down in a way that is natural to us. And all of that has to do, in some sense, with the universe expanding. As the universe expands, the arrow of time is in that direction of the way we see things being natural. If the universe were contracting, in some sense, everything would be reversed, and maybe the cup could turn back into a broken cup could turn back into a full cup.
Okay.
At least if the universe were purely classical, that would be the case. But quantum mechanics actually adds in some randomness to things. It adds in the probabilistic factor. So it wouldn't be quite as exact as I described. Things would not go backwards in exactly the right sense. But time is a complicated thing. It's really tied to how the universe functions. There are theories with one time dimension and 10 spatial dimensions. But we only see 3, and the other 7 are basically compactified into a tiny little object, a little manifold, it's called. At every point in space-time, you have one of these little manifolds that you can't see. because it's just a compactified little space-time of its own, seven-dimensional space of its own. And this concept, as crazy as it sounds, actually has a lot of merit and helps us to understand a lot of things. For instance, it's very difficult for us to understand why gravity is such a weak force. It's incredibly weak. I mean, compared to electromagnetism, because, for instance, it takes a whole planet to hold us down, but we can still jump even, gravitationally. Electromagnetically, if you and I were standing next to each other, and each of us suddenly lost 1% of our electrons, okay, the force between us would be great enough to lift the Pacific Ocean. I mean, it's unbelievable how much force there is in the electromagnetic fields compared to gravity. So why is gravity so weak? And one explanation is that gravity could be the one force that actually goes into these other 7 spatial dimensions. And it looks weak to us because we're only seeing seeing it in 3 of its 10 dimensions. So it's leaking out of our visible universe.
So we're losing gravity to the dimensions.
Yes, we lose the gravity into these other dimensions. And that actually is interesting. You can develop theories based on that help explain a lot of things in the universe. So we're actually trying to find evidence of these additional dimensions at the LHC. We've been looking and looking and looking. And so far, nothing has come up. But it just means those dimensions are pretty small, and we'll keep looking.
And the other thing we talked about last time, I remember this idea of the edge of the universe, and there isn't necessarily an edge, is it? It just goes back around in on itself. And I was quite fascinated by that, really. I mean, it's all theoretical, really, I guess.
Yeah, and this is stuff I'm finding out that maybe my understanding was a little bit behind the times, but it's hard to understand what is the universe. The universe is really, if you like, the universe is what we can see at any given time. It's what is within the range, such that if light was emitted from something far away, that light would reach us. If it was too far away, the light would never reach us, if you like, because light has a finite speed, and the universe is expanding, and so the universe has a visible section of it that we see, and that's really all we see is this visible part of the universe. Now, interestingly, given the fact that the universe is expanding at an accelerated rate, it means that the edge of the universe is falling out of view all the time. So things are moving out of our view, humbling,
but fascinating because it's
fascinating.
Yeah, it's bigger and stranger.
It gives us a lot of work to do in the future, which is also good.